to waste more time, can we get a round of applause for Richard Feldman to come on stage and kind of talk about, what he does these days? Come on, Richard. Let's get a round of applause. A round of applause. Come on, come on, come on, come on. Give it 5. There you go.
We good? All right. Welcome, everyone. This is Escape Hatch Pitfalls. I'm Richard Feldman. So back in the day, like all the way back in the day, you had machine code, and then this new thing came out called assembly language. And it was wonderful because instead of doing punch cards, you could now write text like this. This is moving something into a register. This is really about as low level as you can get with like textual programming. And then fast forward a few years, and eventually you get C. And C is a higher level abstraction than assembly language. It's not usually dealing with registers. That's sort of automatically handled by C. But if you need to, you can drop down into assembly language using an escape hatch. So inside of C, you can basically say, I want to write some assembly right now, and you can just do that in the middle of your C program. Now fast forward another few years, and you get a language like Java. Now Java also has the ability, if you need to drop down into C. So you have another escape hatch there, escape hatch from Java into C, using java.lang.foreign. And if you use this, you can drop down into C, and then putting those two together, if you want, you can have some assembly code all the way inside your Java program. Then also you've got other languages like Scala, which is even higher level of abstraction than Java. And of course, if you're writing some Scala code and you need to drop down into Java, there's a way that you can do that too, using a very similar import statement. And of course, putting all this together, if you want to, in your Scala code, theoretically, you can escape hatch your way all the way down to writing assembly code in Java, in Scala. Quick show of hands. How many people here have written or are currently writing Scala? OK. Hands down. Another quick show of hands. How many people have written assembly language in their Scala? Wow. OK. I was expecting 0, but OK. Very impressive. So this is something that you can do. But of course, although there are a number of benefits to this, like for example, let's say you've got a Scala library that you're looking for, and you say, I can't find this in Scala. Maybe you drop down into Java, and you're like, oh, Java has that library that I need, so we're good. I'm glad I have that escape hatch. Or maybe you're writing some Java code, and you say, I can't get this program to run quite as fast as I need it to be. Maybe I'm going to drop down and write some C code or use some C library for this. Or maybe you're writing some C code, and you need to drop down into assembly. Now, you might say, why would you ever need to drop down into assembly from C code? I mean, it's already incredibly low level. So this is a blog post from a guy named Brian Smith. He's not talking about writing C code here, but he is talking about the need for writing assembly code inside Rust, which also is a language that lets you write very low-level code. Now, he's the author of the most popular Rust cryptography package. And what he writes in this blog post, which is called Rust Cryptography Should Be Written in Rust, he writes that, quote, Rust should be improved. I would like to see Rust be improved to provide the necessary building blocks that are needed to write cryptography code that is free from timing, side channels, and similar hazards. Show of hands, how many people have heard of timing side channels before? OK, a few. So for those who aren't familiar with this is basically the idea that you can attack some cryptographic code, try to break the encryption by observing timing phenomenon on how long it takes to process certain inputs. So you try giving the cryptographic algorithm certain different inputs, and you observe the amount of time that it takes to run. And the idea is that if you're able to observe that precisely enough, you can potentially learn things about what the secrets are underlying that. And the only way to really prevent these types of attacks is by really carefully micromanaging the actual machine instructions that are happening at the lowest possible level. And for this, even in Rust, even in C, you kind of need assembly language. You really can't get away with letting even C do stuff like automatically managing which registers are going where. You need to be micromanaging the registers yourself. That's what Brian's talking about here. So yeah, maybe if you're writing C, you actually do need to drop down into assembly because you're saying, I can't harden this against timing attacks. I need that escape hatch to be able to micromanage this because neither C nor Rust, at least today, has built-in first-class ways that you can do this without an escape hatch. And then if you're writing assembly and you need an escape hatch down to, I don't know, machine code? OK, I'm not sure why you might need that. Maybe you're like, I just missed punch cards. I really want to like do some extremely low-level handwritten machine code. I don't think that's all that realistic. But all these others, it totally makes sense why you would want escape hatches like this. There's definitely value in having them. So having said that, there are some pitfalls. So at least back when I was doing Scala, it was the case that basically all of your collections that you're working with tend to be immutable, and null, although it exists, is something that's really strongly avoided. Now, in contrast, if I'm using Java and I'm doing some Java interop from Scala, if I'm using that escape hatch, now anything can be null. Any object in Java can be null. And many of the Java calls mutate. So this is sort of a pitfall that I have to watch out for if I'm making calls to Java from Scala. Also, if I'm writing Java code, I can expect everything to be memory safe. The JVM has its own garbage collector. It doesn't support direct pointer access, except through very occasional modules that most people don't use. And generally speaking, the code is machine independent. In other words, whether I'm running it on a Mac, or Windows, or Linux, whether the hardware is Intel or ARM, I can expect that it's going to run the same way. This is sort of Java's original selling point of like, write once, run anywhere. I can sort of expect that, but as soon as I start dropping down into C and using that escape hatch, now I have to worry about memory unsafety. I can get segmentation faults, which there is no try-catch equivalent for segmentation faults. There's this whole other separate thing that I have to worry about, and there's potentially machine-specific instructions in there as well. So this whole write once, run anywhere thing doesn't really work out anymore if I'm sort of bypassing the VM and using C code that's potentially doing machine-specific stuff. Then we have C, where stack memory is managed automatically. And again, if I'm dropping down into assembly, now I can do stuff with registers, including registers which control what's going on with the stack. So I can potentially corrupt the call stack and make it so that I am running one function, and instead of that function returning back to where it came from in the original call site, maybe it goes somewhere completely different and breaks the program in new and exciting ways. So this is kind of a recurring theme of this style of escape hatch where you're sort of dropping down to a lower level language. There are these pitfalls you have to watch out for. And the more levels you're dropping down, the more pitfalls you have to potentially watch out for. So these are some of the cons that come with the upside of getting that sort of expanded access to things. Now, having said that, these are all options. These are not requirements. You absolutely can write Scala code without dropping down into Java, without C, or without assembly. There's no requirement that you use this. Just because the escape hatch is there doesn't mean that you have to use it and potentially run into these pitfalls. So here's a question. Can just the option itself have downsides? In other words, even if you're not going to plan on using it, can there be a downside to the escape hatch existing at all? Well, I'd like for you to imagine, if you will, a river. Actually, we're in Budapest. We don't have to imagine a river. We've got a very nice river with like some beautiful stuff on both sides. But this is a more hypothetical river, a metaphorical river. On this river, on one side, we have Node.js, and on the other side of the river, we have JavaScript that runs in the browser, sort of the old school, original JavaScript, not the separate thing that Node.js became later. Now, one of the differences between these two is that unlike JavaScript in the browser, Node.js has an escape hatch. If you want, when you're writing Node.js code or making a Node.js package, you can drop down into C code, just like we saw before with Scala and Java. Now, one of the things that can happen is, even if this weren't already true with Node.js, which to be fair it is, anytime you're running untrusted C code on your machine, it can potentially give you a virus. Now, granted, Node.js can too, without needing to drop down into C. But certainly, if you're running untrusted C code in the same process on your machine, that's just one of the things that it can do, is it can give you a virus. Now, I haven't used the word virus a whole lot compared to how much I did in the 1990s. How many people remember this product, Norton Antivirus? Okay, this is an age test. So back in the day, like the early days of the web, this was super common because what would happen is that since web apps were not really a big thing back then, if you needed to do something non-trivial, in other words, basically any website that was more than just text, like for example, like encyclopedias were a thing back then, booking airline flights, that was not done through web apps either. Back in the day, it was so common to download arbitrary executables that were full of C code or maybe some language that compiled to something that had an escape hatch into C, that really it was very common to get viruses from stuff you downloaded from the internet and then ran on your machine. Norton Antivirus was one of the most popular solutions to this, or attempted solutions to this. And one of the reasons that we don't deal with this so much anymore, and viruses are not as big of a concern as they used to be, is the fact that there are so many web apps now. If I go to example.com or whatever website, I can expect that it's running HTML, doing rendering based on that, it's running CSS, and it's running some JavaScript, but that JavaScript is sandboxed. It doesn't have the full capabilities of writing to the file system, potentially putting viruses there like Node.js does, and it doesn't have an escape hatch into C that would let it do that too. But imagine if it did. Like imagine if someone said, hey, we've introduced this brand new feature, it's really great. Now, the JavaScript that runs in your browser can also drop down and use an escape hatch and run C code. Isn't this wonderful? You now have the option that you didn't have before. Now, that might sound like, oh yes, that's great, but to me that sounds horrifying because now that means anytime I visit a website, I can potentially get a virus from it, and we're right back in the 1990s, except now we need like Norton Antivirus for Chrome or something like that. So this is not really a world that I want to live in. This is not an escape hatch that excites me. And I think, oh, that's really good. So thankfully, we don't live in that world. Instead, we live in the world of sandboxing, where there is a 100% guarantee that not only can the JavaScript that runs in my browser not modify my file system, it doesn't have an escape hatch that would let it do that. So this is sort of a broader sort of pattern of, on the one side of the river, you have escape hatches, and on the other side, you have guarantees. And you sort of have to pick one. If you make the escape hatch, then you sacrifice the guarantees. You cross from one side of the river to the other, and you're now just in a different world. So on this example, we have the guarantee of sandboxing that you get from JavaScript in the browser, and the escape hatches, granted, they do get you some benefits. The fact that Node.js has the escape hatch into C means that you get access to the whole C ecosystem. If there's some package that doesn't exist in Node, but there's a C library that does that, you can get that and sort of seamlessly use it and not be blocked on not having access to that. Also performance. Node.js has gotten a lot faster thanks to V8 and stuff like that, improvements in that, but it's still not as fast as what you can get if you're writing C or some lower level language. So that escape hatch means that the performance ceiling on how fast your Node.js programs can run does get higher. And also there's that level of control. And like as we saw with the cryptography example, sometimes the only way to get the level of control needed to implement certain primitives in a safe way is to go all the way down to assembly language, and there's really no way you can write the same equivalent of that in plain old JavaScript that's running in the browser. This is one of the reasons that people recommend against sort of rolling your own crypto implementations in the browser in JavaScript. There's just no way to really practically secure that against timing attacks because, at least today, the only real way to do that is to go all the way down to assembly language. Okay, so here's a question. Can we get all of these? Can we get the best of both worlds? What if there was no river separating these two? What if we could get ecosystem and performance and control and sandboxing all at the same time? Well, we can't necessarily get 100% of all of these things. I mean, obviously, if there were some magic wand you could wave and say, I'm going to get all the entire C ecosystem and performance and control and sandboxing, that would be wonderful, but unfortunately, these are trade-offs. What we can do is we can get a subset of the benefits without sacrificing the guarantee. So this is one of the things that WebAssembly does. So WebAssembly is, if you haven't heard of it, it's a technology that runs in browsers but doesn't necessarily have to run in the browser. And it's not really an assembly language, it's actually more of a virtual machine, so it's sort of a layer above the machine code. The joke is that WebAssembly is neither assembly nor really tied to the web, but nevertheless, that is the name that they went with. Now, in the case of WebAssembly, you cannot execute all the way down to individual assembly instructions that are machine dependent, so you can't mess with registers in particular. So that level of control that we were talking about that you would need to implement cryptographic primitives, that's not something that normal WebAssembly does. There are some researchers who pointed out this deficiency and like, hey, it would be really great if you had the ability to do these things in WebAssembly. They made it something called CTWASM, which is short for constant time WebAssembly, that lets you sort of implement WebAssembly code in a way that's resilient to timing attacks, but that's really not a mainstream like WebAssembly implementation. It's more of a research thing. So I'm going to say that if you're using WebAssembly in practice, that's just one of the benefits you're going to have to give up compared to the escape hatch world. So what about ecosystem? Well, you definitely can take C code and compile it to WebAssembly. Usually. Sometimes. Not all the time. Obviously, as we talked about, C can drop down into assembly language, which means if you've got some C code that is running some machine-specific assembly instructions, those assembly instructions can't be translated to WebAssembly because WebAssembly is running in a virtual machine that's a layer above that. It just doesn't support manipulating registers at that level. So some of those C programs, they're just not going to be able to compile directly to WebAssembly, or if they are, you have to have some sort of transpiling workaround kind of a thing that maybe will work out, maybe not. So let's say you've got some sort of subset of the C ecosystem. There's other reasons that C code might be incompatible with WebAssembly, but you can get a whole lot of C libraries that will genuinely just take it, run it through a C compiler, and just spit out WebAssembly on the other side, and you're fine. So that's great. Performance, I'm going to give it 4.5 rocket ships out of 5. So it's not quite as fast as just compiling all the way to machine code because there is that virtual machine layer on top that needs to do a little bit of extra compilation to get all the way down to machine code. But it's a lot faster than pretty much any of the higher level alternatives, such as JavaScript, Ruby, Java, C#, things like that. So what we can see here is that we're not getting 100% of what we would get with the escape hatch approach. The escape hatch gets us the entire C ecosystem, all the maximum performance, all the control necessary to implement even crypto primitives, whereas what WebAssembly gets you is the sandboxing. So they have managed to maintain 100% of the sandbox. This is why we're not hearing about people getting tons of viruses due to WebAssembly being added to browsers. They did very carefully make sure that the entire sandbox is maintained. So you get that really, really critical benefit. People can still visit websites without fear of viruses, and yet we still get not 100%, but a very, very large proportion of the benefits that otherwise could only be obtained using an escape hatch. So this is a really tricky thing to do, is like adding power, especially this much power, while maintaining guarantees. There's a reason that WebAssembly didn't ship with browsers in 1995. Partially it's because they didn't necessarily realize there would be demand for that, but also it's just because it took a long time to develop the spec, figure out all the technical concerns, and also, of course, get all the browser vendors on board. So this is also a recurring theme, is oftentimes the escape hatch is very quick. You can just be like, throw it in there, and you're good. If you want to try and maintain the guarantees on the other side of that river while still getting a lot of the benefits, maybe not 100%, it usually takes a lot more care and design, and it's not usually necessarily something that's going to ship with the first version unless you're okay with delaying the first version to get that. But on the other hand, we can see there's some pretty big benefits if you do go with that route instead of the escape hatch route. How many people here use NPM? Okay. How many people here use NPM not for Node.js, but rather for like in-browser JavaScript, like dependencies? Okay, not as many, but still quite a lot. So this is an extremely popular way to get dependencies. Obviously, originally it was the Node Package Manager. I've now been told that apparently NPM no longer stands for Node Package Manager, but come on, we all know what it originally stood for. And when you run npm install, this will install your dependencies. It'll download your dependencies and your dependencies and whole lots of dependencies. And that's true whether or not you're installing Node.js dependencies or browser-based dependencies like, for example, React. Now, if I'm installing a browser-based dependency, it might be reasonable to assume all it's going to do is it's going to download some .js files and just put them into some directory, and then now those are part of my bundling process or whatever I'm doing to build my front-end code. In other words, I might think that, well, because I'm just installing React, I'm still sort of getting the same basic sandbox experience here. I'm not really worrying about the fact that, yes, technically Node.js can give me a virus and all that, because it's React. It's not Node.js code, it's browser-based JavaScript code, and the browser's got a nice sandbox around it. Unfortunately, there's that install thing. And inside the install process, there's a thing called a pre-install hook and a post-install hook, where any package that you install can execute arbitrary Node.js code on your machine, which means that it's executing potentially arbitrary C code on your machine because of the escape hatch, which means you can very definitely get a virus from doing npm install on anything. And not only that, but unfortunately, you can get it not only from the thing you're trying to install, but also any of its dependencies. So if I install a Node.js package or a JavaScript package from npm, and it's got a dependency of a dependency of a dependency of a dependency, and that one gets compromised by someone, guess what? I might have just gotten a virus. Unfortunate. Unfortunately, especially unfortunately, lots of people are taking advantage of this. So here's a headline: 48 malicious npm packages found. This is from 2023. Hundreds more packages found in malicious npm factory. Malicious npm packages are part of malware barrage. Yeah, it's really unfortunate. I think we all know what the solution is here. We just need Norton antivirus for npm, and then every problem will be solved. Yeah, unfortunately, this is a real thing that really happens. There are really like attackers out there trying to compromise people's packages, especially weird tertiary dependencies, or trying to sneak weird tertiary dependencies in through sneaky pull requests, which they then will change the dependency and publish a new version that claims it's a patch version, but actually it's a patch version that gives you a virus. Because this is just a viable attack vector because of all these escape hatches. So there is, fortunately, a much better solution than Norton antivirus for npm, which is if you run npm config set ignore scripts true, which is something that I always try to run as soon as possible after installing npm on a new machine, this changes that default and says that by default, now whenever you run npm install or install any package, it's going to not run the pre-install and post-install scripts. Now, for most npm packages, this is totally fine. Unfortunately, there are some that just genuinely actually don't work unless they are able to run the pre-install and post-install hooks. So I can't promise that if you run this, like all of your problems are going to be solved and you're not going to have any issues whatsoever. There's probably going to be the occasional package where you need to sort of opt out of that. But I do feel a lot of peace of mind by having this set by default, because I know that it means I'm not running essentially arbitrary C code on any dependency that I've ever used or that any of my dependencies are using every time I run npm install. Okay. Now, on the other side of the river, there is a way that you can do package management that doesn't have these escape hatches, that's more with the guarantees. How many people here are familiar with the Elm programming language? Nice, okay. So this is a programming language that is designed for front-end web development. So the website says, a delightful language for reliable web applications. I would agree with both parts of that. I would say it is a delightful language. I've spent a lot of time with it and had a really great time. And it is really good at making reliable web applications. Now, Elm has its own package manager. It's completely separate from NPM. Elm compiles to JavaScript, but it doesn't really share a lot with the JavaScript ecosystem. This is what the Elm packages website looks like. It's totally separate from NPM. And Elm packages has a sort of different set of rules and policies for what happens when you install a package from it. This entire package repository, it's all Elm code. There is no Node.js. There's no pre-install hooks. There's no post-install hooks. When you install your Elm packages, it's just downloading Elm code and putting it into some directories for you. It's not running any of that arbitrary code, so you don't have to worry about the whole like node to C to viruses pipeline. That's more of a concern when you run npm install. There's no default that you have to change. It just doesn't exist. No, there are trade-offs here. Because npm supports those things, it does have more options. There are certain packages that can exist in the npm ecosystem that just cannot exist in the Elm ecosystem. And much like with the sandboxing, the trade-off is that you get a more reliable experience. I've never had any concern about installing Elm packages. They always just kind of work, and it's fine. Whereas with NPM, there is always this fear that I'm going to be part of one of those headlines. RubyGems is another package manager that's different from NPM, but for the Ruby programming language. How many people have used RubyGems? OK, cool. So one of the things that happened to me at one job I was working at where we were using RubyGems was we were installing a package called the Ruby Racer. Has anyone here ever installed this one? OK. Not as many people. So the experience that I got when I did this, and I actually went on Stack Overflow for this talk, and I found that somebody else had had the same experience, is I got a message like this when I was trying to install the Ruby Racer. This is some C++ gibberish. I remember seeing this and thinking, I have no idea what to do here. Why am I getting C++ errors? I'm just trying to install a Ruby package. I'm not here to write C++ code. I don't know what's going on. Help. And this is a pretty negative experience. I mean, Ruby's a language that is well known for having a pretty nice developer experience in a lot of cases. This was not one of those cases. So why did this happen? This happened because one of the things you can do in RubyGems is you can have an installation process that will build things from source, including things like C and C++ code. And the reason that the Ruby Racer needed to be building this code, or decided to be building this code, is that the purpose of this package is to, quote, embed the V8 JavaScript interpreter into Ruby. So the reason you might want this is, let's say you're building a web application, and you've got some HTML that you're generating and some JavaScript that you're generating, and you just want to write some tests that are actually using a real JavaScript interpreter that is baked into people's browsers, V8 being the interpreter that powers Chrome. So you want to be able to sort of test things, write Ruby code to describe your tests, and then have it run in an actual browser, like a headless sort of version of that, to see if it's getting the outputs you expected. So it makes sense why they would do this. And of course, if I were in a package manager ecosystem like Elm's, there's just no way this is going to work. I mean, how would you possibly, if all you're doing is downloading Elm code, are you going to re-implement V8, which is a gigantic millions of lines of code C++ code base in Elm? Of course not. Even if you tried to do that, because Elm compiles the JavaScript, it's probably going to be horrendously slow and not a really great experience for writing your tests, because it just doesn't make any sense to try to implement a code base like that, an entire browser, in a language that's compiling to JavaScript. So it's completely understandable, on the one hand, why RubyGems would choose to do this, even though it did ultimately lead to my having a pretty bad experience when I was trying to install it. So again, we have the theme of more options. This is something that's possible because RubyGems supports this, versus more reliable. I've never gotten any C++ errors when installing Elm packages. Another trade-off. So I've been working on this programming language called Rock. How many people have heard of Rock? Awesome. So Rock is a programming language that bills itself as a fast, friendly, functional language. It's inspired by Elm. It's a direct descendant of Elm, but it covers a different set of use cases. So whereas Elm is very focused on web applications, making delightful web apps in the front end, Rock is sort of for like the long tail of other use cases besides that. So Rock does not compile to JavaScript. It compiles to either machine code or WebAssembly. And it's designed to be sort of fast in terms of fast performance, fast compile times, friendly in terms of user friendliness, and of course, functional language like Elm. Rock is a purely functional language. So the Rock package manager has a lot in common with the way that Elm does things. So for example, it does just download Rock code, but there is one slight exception to that. In addition to downloading a bunch of Rock code, it also downloads exactly one binary. And that one binary could be written in C, C++, Rust, Zig, whatever low-level language you like to use. Now, this does mean that for that one dependency, you do potentially have all of the concerns that we've been talking about here. You could definitely get a virus from that. There's all sorts of bad things that could happen from that one thing, because it is running completely untrusted C, C++, whatever code. So you do need to worry about that for just that one dependency. Importantly, it's exactly one. So it's not the case that you have to worry about some dependencies, somebody sneaks in something very carefully and manages to give you a virus that way. It's just really this one dependency that you need to worry about. So on the one hand, compared to Elm, you don't have this guarantee of like it's always going to be fine. But on the other hand, you have a way, way smaller surface area of things that you need to be worried about when you're installing rock packages. It's really just the one. So let me explain what I mean by that and why it's exactly one. So in a typical rock program, in any rock program, you have it broken down into two parts. So this is unlike most programming languages. Every single rock program has two parts to it. One is called the application, and the other is called the platform. So the application is something that you might think of when you're just writing a program in any language. So like here's hello world in rock, this is hello.rock, say main equals sit-out.line, hello craft. So when you run this, it'll print that out to standard out. Now the difference is that in most applications, like if I were writing this in Python, that would be the end of the story. I would just say, here's my application, here's whatever.hello.py, and then I would just run it. The difference is that in Rock, you always have to specify. Every application has to say, I am built on this specific platform. Now a platform is kind of like a framework in that it's sort of domain specific. So for example, you can have platforms for like building a command line app. You can have a different platform that's for building web servers, and a different one that's for building games, and a different one that's for building editor extensions. There's a long tail of potential platforms you can have. So for this particular example, I would definitely, for Hello World, I would pick a basic command line app platform. So the most popular way to build command line apps in Rock today is a platform called Basic CLI. And essentially what the platform defines is it defines sort of all of the basic primitives that you're going to need for working in that particular domain, in this case, command line apps. So for example, Basic CLI is going to define standard out.line. Like what does that mean? When you run that, you want to print the standard out. How is that implemented? And also the platform, and this is where that one binary comes in, the platform also provides the implementation for that. So in this case, Basic CLI happens to be implemented in Rust, but that's just an implementation detail. It could have also been C or whatever else. Now importantly, in Rock, the standard library of the language doesn't include any I/O primitives at all. All the I/O primitives come from your platform, whichever one you pick. And you might get a different set of I/O primitives depending on which platform you're building on and what use case you're targeting. For example, for a command line application, you definitely can write to standard out and then also read from standard in. But in a web server, it doesn't really make sense to read from standard in. Like, why do you want your web server to like block a request handler on like stopping to read from standard in? That doesn't really make sense. So you get this sort of specialization of the I/O primitives depending on your use case, and the platform provides all those. Now, there's another really important implication to platforms providing all the I/O primitives, which we're going to see in a sec. So if I run rock hello.rock, essentially it's going to do kind of the npm install type stuff in the background for you. You don't really need to worry about that. So when I run rock hello.rock, what it's going to do is it's going to say, okay, which platform have you specified? I didn't show the code here, but somewhere else above this in hello.rock, it would specify which platform I'm using. It's going to go download that platform. So it's going to say, hey, I see that you're specified Basic CLI, which is available at this URL. I'm going to go download the rock code for Basic CLI. And also, I'm going to download the exactly one binary, which is that compiled Rust code that provides all those I/O primitives and all the basic stuff that you need for building a command line application. So this is the entire surface area that you need to worry about, is the platform. You don't need to worry about any of your other dependencies because they're not capable. They're not allowed to have an escape hatch into C or anything else like that. It's just the one thing. You got to trust your platform, and that's it. And then, of course, after all this stuff is sort of happening in the background, it's going to run and print hello craft. So the idea here is that as an application developer, this mostly feels like just using a Python or a Ruby or a Java or something like that, except with full type inference and lots of other niceties. Except that you do have to specify there's this one little extra bit of housekeeping where you say, and by the way, here's the platform that I'm running on. Okay, now where this gets cool is what happens if you're doing something more advanced than hello world. So for example, let's say I have downloaded from the internet a file called setup.rock. Somebody else wrote this. I don't know them. I want to run this rock script. Also, this could be something that was generated from a large language model. Like we've been talking about generative AI a lot at the conference. That's another untrusted source. Like it's been spit out. I don't know what's in there. Maybe there's something malicious or maybe there's something accidentally that's going to cause problems to my system. The point is, I've downloaded this script from the internet and I'm going to run it. Now, I'm not going to ask for a show of hands on this one, but I bet we all know, we have all done this, where we downloaded something from the internet and we knew that it could potentially mess up our system. It could potentially give us a virus. It could potentially do all sorts of bad things. We didn't want to read all that. Come on. It's just like, there's so much code in there, right? I mean, after looking at like the platform in Rock's case, you might see this long main. It's doing file.download, and if do this, then that. And there's a bunch of lines of code, and then at the very end, it prints out done. And I'm just not going to look at all that. I'm not going to look at its dependencies and audit every single line of code in there, especially because, honestly, if there is an attacker, they're probably going to do their best to obfuscate that anyway and try to prevent me, even if I am scanning through and trying to read all this stuff, try to prevent me from noticing that they're doing something sneaky. There's a common trick of like base 64 encoding and decoding things and doing eval and whatnot. There's all sorts of tricks attackers will do to try to obfuscate this type of stuff if they're trying to actually give you a file that's malicious. Okay, so let's say that I run rock setup.rock and it prints done. I don't really know what it did in there. Like, hopefully it didn't do anything malicious, but I have no idea. I didn't read all this code. Hopefully it didn't do anything, but it very well might have. Now here's the cool part. Let's say that I do nothing else, but all I do is I change that one line where the platform is basic CLI, and I change it from basic CLI to safe script. Now this is something that's not out yet. People are still working on it, but the basic idea of safe script is that it's a drop-in replacement for basic CLI. So it has all the same APIs, all the same file.download and standardout.line and all those types of rock functions. What's different is the implementation behind the scenes. The platform is different. The underlying Rust code that runs all of those I/O primitives is completely different in safe script. And the way that it's different is it introduces sandboxing. So let's say that I run rock setup.rock, and now I've changed it from basic CLI to safe script. Now it might do something else before it prints done. It might say, for example, hey, this script wants to download evil.com/malware.zip. Do you want to allow this? And I can be like, no, why? Obviously not. That sounds terrible. Or maybe it says, hey, this script wants to read from etc password. Is that cool? Does that make sense for setup.rock to do that? And again, I can say, no, I don't want that. The point is, this is the same type of sandboxing you get in the browser. Like, the browser will often prompt you before allowing webcam access or something like that. It's the same kind of thing with the file system. If I'm running untrusted code, I want to be able to say, like, oh, I see that you're trying to do this potentially dangerous thing. I want to know about all that. And I want to have the opportunity to say, no, actually, I don't want this script to be able to do that. So it doesn't matter how obfuscated the code is. At the end of the day, where the rubber meets the road is, does the script have actual access to do this? And here's where it's really important that there is no escape hatch. Because if I have safe script, and it is in charge of almost all the I/O primitives, except that, oh, by the way, any rock script can just do arbitrary CFFI, then it doesn't matter. Because, of course, an attacker's going to use that. They're going to use the escape hatch maliciously. They're going to use it to just bypass all this stuff. And that's why it's really important that rock does not have that escape hatch. In order to get this benefit, it only can happen if we're on the other side of the river. If we have the guarantee instead of the escape hatch, and every single I/O primitive is implemented by the safe script platform, there are no exceptions, there are no escape hatches. That's the only way to get the benefit. By the way, this also extends to any packages they might have. So in addition to the exactly one platform, applications can also say, I want to have this package or that package. These work the way they do in most languages. It's like, you get it from the internet and it downloads it, puts it on your machine, and so forth. But all of these packages, they cannot do CFFI. They don't have that escape hatch. They're only allowed to just be more rock files. So at the end of the day, it doesn't really matter how many dependencies my thing has. I don't really care. There's nothing that anyone can sneak in that's malicious. Safe script is going to be protecting me because any of those dependencies, they're all going to have to go through that same I/O implementation of that one platform, and it's going to prompt me if they want to try and do anything malicious. So going back to our river here, on the one hand, we have NPM, potential for viruses, but there are more options. On the other hand, we talked about with Elm, it just downloads the Elm code. It doesn't run any pre-install or post-install stuff. It doesn't run Node.js code, doesn't run C. That is more reliable, but of course, it's also more limited. Rock is somewhere in between. So you do have more options. There is that access to that full C ecosystem. This is not WebAssembly. It's not like we have the subset of that is able to compile to WebAssembly instead of assembly. The platform really can do absolutely anything. It can go all the way down to individual assembly instructions if that's what that platform author wants. But importantly, from a surface area perspective, you only have to trust that one dependency instead of that dependency and all of its dependencies and all their dependencies. So this is more reliable than what you get in NPM. There's less of a concern there, but it's still not as many options as NPM, and it's not as reliable or as little concern as what you get from Elm. So in other words, this, much like WebAssembly itself, this is another example of a way that you can sort of add power while maintaining guarantees. This is one of the design goals of Rock, is to do that on purpose. Now, we also talked about this example with Ruby gems in the Ruby Racer where I got this really nasty C++ error. Well, this is another example of where you have a use case embedding the V8 JavaScript interpreter into Ruby that, again, this just sort of requires some amount more power because much like you're not going to write V8 with millions of lines of C++ code in Elm, you're also not going to do that in Rock, even though Rock can run faster because it's compiling to machine code instead of to JavaScript. That's still just not a project anyone's going to do. But what you can do in Rock is you can have a platform that has V8 built into it. Because again, the platform can do whatever it wants. So it's absolutely in scope to make a web development platform that ships with a V8 interpreter built into it. And now you actually can write your tests in Rock that are actually running on a real browser and doing all that stuff just like you could in Ruby. The difference is that this is sort of the equivalent as if, like, what if in the Ruby side you had Rails and Rails came bundled with a V8 interpreter? So it's like if you combined Rails and the Ruby Racer. And whereas in Rock, you would say, I'm going to make a web server platform, I don't know, Rock, Rails, something else, you come up with some name for it. And part of the selling point is this ships with V batteries included of a full, nice, complete testing system that actually runs a real browser and interprets your JavaScript for you. So again, this does give you more options because Rails is not smashed together with the Ruby Racer, you can swap it out for a different one. If instead of V8 you want a WebKit thing, whatever, you have that optionality in Ruby gems that you don't have in Rock. But again, this does give you something that's more reliable. So we're not building any C++ code from source. The platform is already pre-compiled down into a binary. So one of the reasons that we have that as a design is that way, whenever you're installing your platform, you're never going to get one of these C++ build errors because it's not actually building any C++. So again, you can get a little bit of a better experience, but there is this trade-off where you don't get quite the same level of flexibility as you do that sort of comes with that potentially degraded user experience. If you want to learn more about Rock and all these platforms and application use cases, I gave a whole talk about it called The Edges of Cutting Edge Languages, and this is like a screenshot from that talk where among other things, I demo the safe script thing, and also there's some other stuff that I'm not going to get into in this talk about how platforms can do their own memory management to make things run faster and do cool logging things and whatnot. But at any rate, if you want to learn more about it, that's a whole different talk. Okay, now so far, we've talked about language interop, we've talked about package manager policies and things like that. But I'm guessing, if you're like me, this is not what you do in your day job. Rock is something I do outside work. It's not my main job. It's definitely the type of thing that I really enjoy. But at the end of the day, really, most of what I spent my career on is just normal application development, web apps, things like that. Actually, shout out to Zed Industries. I'm about to start there in a couple weeks working on the Zed editor. If you want to check that out, it's zed.dev. Very excited to do that. The point is that most application development is not dealing with language interop. It's not dealing with package manager policies. So I'd like to wrap up by sort of talking about that type of stuff. Because as it turns out, all the stuff we've been talking about is totally applicable to normal application development. For example, here's something we do all the time: hiding implementation details. Bread and butter software engineering type of stuff we do all the time. For example, let's say we've made a data type and we've made its internal structure private. So now we can change it in the future without breaking all the call sites. Or we're making an API, and this is a publicly exposed API, but we're only exposing certain things. We don't want customer secrets to leak out, stuff like that. Totally a reasonable reason to hide implementation details, or maybe just an individual module where we're saying we've got some internal helper functions that we might want to change in the future, so we're intentionally not exposing them. Now here's a show of hands. How many people have ever intentionally hidden an implementation detail, and then somebody else, maybe a coworker, or maybe yourself later, comes up and says, hey, can you add an escape hatch to expose just part of that? Yeah, right. It's a thing that happens, right? And usually there's some, if you say no, you kind of push back on that. There's some follow-up there, like, well, look, you already implemented the functionality. It's right there. Look at that code. It already does exactly what I want. Just expose it for me and I can use it. What could be the downside? Or they might say, you say, well, look, I want to be able to change this in the future. If I expose it, it's potentially going to break stuff. They say, look, I'm an adult, okay? If it changes, I'll deal with it. Don't worry, I promise. And you're kind of thinking, yeah, but what about all the other people? Whatever. The point is, this type of thing happens all the time. And to be fair, like we talked about, there are absolutely benefits to choosing to add the escape hatch. Sometimes it's the correct course of action. Sometimes it might just be a matter of convenience. It's like, look, we got to ship this thing. We're going to add the escape hatch now because that's going to let us ship faster. I get it. That can happen. Or maybe you're like, look, this is just going to give us more functionality without having to re-implement it. It just makes more sense to break that abstraction layer. Or maybe it's even just faster performance. It's like the publicly facing API that hides these implementation details. It's just not as fast as if you expose part of the implementation details. That's just going to let us go faster. I get it. But at the same time, if there's only one thing you take away from this talk, it's that there is always another side to that river, always. And if you don't know what guarantees you're giving up, if you can't say, here's what we would be giving up if we added that escape hatch, it's because we don't know. It's not because they're not there. They're always there. There's always something you're giving up. That's why we call it an escape hatch and not the main door. The question is, what are we giving up? And that's the thing we always have to ask ourselves whenever we're considering adding an escape hatch. Even if we do ultimately decide that it's the correct course of action to add it, it's really important that we've thought about what are the pitfalls, what are the guarantees that we're giving up in order to add this thing. And as we've seen, if you ask that question and you try to think really hard about, is there a design that we can use to add power while maintaining these really critical guarantees, this isn't exactly the best of both worlds, but it can be way better than just going for the quick answer and just saying, you know what, we're just going to throw the abstraction boundary out the window and just say, here you go. Here, just use this escape hatch. You can sometimes find designs that let you maintain those guarantees or the critical set of guarantees, even if it's not exactly the set of guarantees you had before, while still adding, hopefully, enough power to cover those use cases, to get the functionality you need, the performance you need, whatever the case may be. But oftentimes, the sort of the cost of doing this is that it does take some more design work. You have to think a little bit more carefully about the problem. And instead of just giving a knee-jerk reaction of saying like, yes, I will add that escape hatch, or no, absolutely not, deal with it. You might say, okay, well, hang on, let's figure out what is your use case? Like, what is it that you need? Why do you want this escape hatch? What would you use it for? And then think, is there some way that we could introduce that power without sacrificing the guarantees that we've worked so hard to create with the existing API? I think if you're able to do that, then you can avoid the escape hatch pitfalls and get a much better outcome for you and your team. Thanks very much.
All right. Hello, hello. All right. Thank you, Richmond. And we got a couple of questions. I think we got a minute or so.
Few minutes for questions?
Yeah, let's go for it. All right, the first question. It's kind of like all right, the first question. So Rock basically uses dependency injection to provide you the standard library, question mark?
In terms of I/O, yeah, that's essentially right. We're kind of in the process of changing how this works, so I don't want to describe exactly how it works, but conceptually, dependency injection is a really good way of thinking about it. And this is, again, just for I/O primitives and things like that. There's a lot of cool stuff that comes with that, with this design, such as, for example, you don't have to worry about, like, oh, do I need to mock this? Do I need to monkey patch that? It's just like, well, if dependency injection is kind of the only way to get the I/O primitives, then everything you use and all the dependencies you use are very instantly testable. So this is something I consider to be one of the benefits of the language, even though it might sound like an inconvenience at first.
And one last question. Most companies require careful dependency analysis already. Why should we give up our options?
That's a great question. I mean, the short answer is that on the one hand, you have dependency analysis where you're saying, look, I'm going to go through and vet all of my dependencies and try to make sure that they're not malicious and have protocols for all that. On the other hand, you still cannot, you can sort of asymptotically approach the guarantee of like, you don't have to worry about this. But you can never quite get all the way there. So this is sort of the pitch for Elm's approach of saying like, you do not have to worry about this. There just is no possible vulnerability there. On the other hand, with something like Rock, you can say, look, I'm not giving up all the optionality. I'm just saying, look, I have one dependency to vet. The platform is the one that can potentially give me the viruses and do all the bad things. Everything else I don't need to vet because all of their capabilities are completely limited and gated by the sandbox that the platform provides. So I just have a much, much smaller surface area to audit. Obviously, we can agree, I hope, that if you are going to go with the auditing approach and try to use that to protect yourself, having less to audit is a benefit.
All right.
We have a couple more.
Yeah. So we can go to the next one. What if I, for example, what if I need, for example, a web server with basic CLI functionality as well? Would I need to create a merged platform?
That's a good question. So essentially, part of the trade-off that we're choosing with this platforms and applications design is that it is up to the platform author, whoever's making the platform, which could be you, by the way. You can absolutely make your own platform and your own application if you want, is that the platform is completely in charge of the experience. So what that means is if, let's say I'm using a basic web server and I'm like, look, I really want this piece of functionality from basic CLI, there's basically one of two paths. One is you can go to the author of that platform, if it's not you, and you can say, hey, I really want you to add this particular feature, and then we get into the whole discussion that we were just talking about around like, okay, is there a way that they can introduce that feature, give you that functionality without breaking the rest of the experience? Or you could just ask them to add an escape hatch. So a common way that you can do an escape hatch in a platform is you can say, hey, I want this platform to give me the ability to run arbitrary C code like through a dynamic library or something like that, where I pass in the string and some way to encode and decode stuff to and from it, and they can just run that library or maybe in a separate process. And now you can essentially add whatever functionality you want. But as we've seen throughout this talk, there's trade-offs to adding escape hatches like that.
And then maybe one more question. Couldn't one interpret basic CLI as an escape hatch for safe script?
I wouldn't say so, because the key thing about an escape hatch is that it lets you use the thing that you're already using in a different way. So basic CLI, in contrast to safe script, you can't both be using safe script and basic CLI. You either have to change your one platform line from basic CLI to safe script or the other way around. You can't really be running both at the same time. So yeah, if you're using safe script and like you want something that exists in basic CLI, that shouldn't really happen since it's supposed to be a drop-in replacement for the other one. But in a hypothetical world where that did happen, you'd have to switch. You wouldn't be able to just say, actually, I'm still using safe script, but I use this escape hatch, and now I'm using basic CLI instead somehow.
All right, another round of applause for Richard, please. Thank you so much for coming down, sharing your